this is our final lesson on probability, and it's actually something that you've seen before. I'm just going to define it more clearly, give you some notation, and expand on the format in which you've seen it. So it's something called conditional probability. So conditional probability means that it's the probability of some event conditional upon another. So it's the probability of a given event given that B is true, given that another event, maybe event B, and the notation we use for that is the probability of A given B. Okay, so we've seen that before when we look at contingency tables. So here's a contingency table that we might have seen. So below is a 2x2 contingency table. We're looking at whether or not students have cell phones and what grade they're in. Now this may have been something more like in, I don't know, 2004. Not the current age, since everybody would be yes. But let's say this is in the year 2004. Okay, this may have been true in 2004 or maybe even later, 2008. So here is some data of a sample of 118 people on whether or not they have cell phones and what grade they're in. So the first question is asking what percent of students own a cell phone or are in 12th grade. Now this is not conditional probability. This we've seen before, and we would use the notation for or meaning add, and this being or. So we would say what percent of students own a cell phone, so yes to cell phone, or are in 12th grade. Okay, so we can answer a question like this, and that would be adding for us. So yes to cell phone is 109, plus yes to 12th grade is 53. But don't forget there are people that have been counted in both of these numbers and are now double counted. So 50 people said yes here and are counted in this number here, so we need to take out the double counts. And so that is 112 out of the 118. And you can find that decimal as well. And get 0.949. Okay, now this next one, what percent of 12th graders own a cell phone? In this case, we are given that we have 12th graders. So this is when we would use that conditional notation, and this is how we've seen it before, of 12th graders. So we are given that they're 12th graders. What's the probability, or what percent own a cell phone? Okay, so in this case, we're going to use this conditional probability where our denominator is the 12th graders because we're only looking at 12th graders. So our denominator is the 12th grade, which is 53 people. That's our denominator. Isolate the 12th graders. And now of those 12th graders, how many own a cell phone? Of those 12th graders, 50 own a cell phone. And so this would be our proportion, and therefore our proportion is 0.943. Now, you might be asking, well, okay, how did we get that? Well, the B, the one on the right, the given, is our denominator. And then the numerator is, given that the 12th grade is true, what's the probability they also own a cell phone? So it's where they overlap, it's the and section. The yes to cell phone and the yes to 12th grade. So it's the and is on top. So this is conditional probability. We have our given as our denominator and the overlap as our numerator. So this says if you don't own a cell phone. So given, this is the given on the right side. Given you don't own cell phone, what is the probability you are in 11th grade? So our denominator is all the no cell phones. So I go to my chart and I look for no cell phones. There's 9 of them. What's the probability they're in 11th grade? So now I'm looking only in this row, and I'm looking for the no cell phones that are in 11th grade. 6. Where they overlap. So we're saying the probability of no cell, and then the both on top. That's this. Okay. All right. What is the probability of an 11th grader owning a cell phone? Again, we're given something about the subject, and therefore that is our given. So now we're given 11th, and we want to know own a cell phone. So given 11th out of all the 11th graders, where do they overlap? So yes and 11th, 59. Okay, and so this is conditional probability with a table. Technically, we've seen it before, but now we're seeing it again with this notation. And we've also seen this before. Is owning a cell phone independent of grade level? And so when we saw this before, we would look at our conditional distributions. We can still do that. We can look at those conditional distributions and see if they're the same. So 59 out of 109 and 50 out of 109, 0.54, 0.46, 0.67, 0.33. These distributions are not the same. 54% is lower than 67%, so it is dependent. Okay, but we do know that independent means that one event does not affect or does not depend on the other. I think it's affect, excuse me. So because of that, what we're saying is, okay, well, the probability of having a cell phone, does that change once we know if we are given we're in 11th grade? All right, if these are the same, then we know that one doesn't depend on the other. So the probability of having a cell phone, is it the same as the probability of having a cell phone given 11th grade? So if they're the same, then we know that having a cell phone doesn't depend on your grade. But if they're different, then we know that having a cell phone does depend on your grade because it is affected by your grade level. So what I'm going to do is I'm going to find these two different probabilities. So the probability of yes, 109 out of 118. The probability of yes given 11th. So given 11th, that's 65. And yes is 59. So 109 out of 118 is 0.924. And 59 out of 65 is 0.908. Those are different percents, and therefore it is dependent. So the probability did change. You are a little bit less likely to have a cell phone if you are in the 11th grade. Okay, so it's dependent because less likely to have a cell in 11th grade in 2004. Okay, so we've kind of seen this stuff before. I'm just introducing it with a little bit more notation. All right. Now, you might also see this in one other presentation, and that's in a way that's not like this, right? It's not in a table. It's just a bunch of words, and that's pretty new. So you might get something that looks like this. You can pause the video and write this in your notebook. That might be helpful. But this is what we're going to work with. An experiment was performed to test the efficiency of a cold medicine. Half the participants were given the cold medicine, and half were given a placebo. They found that 80% who were given the medicine were cured after a week, but they also found that 25% of those who took the placebo were cured after a week naturally. So what we need to do is figure out how we can organize this information into something that kind of makes a little bit more sense for us. So what we do actually is we can create something called a tree. And so you can kind of see the tree. What we're going to start with are these two branches. You can have as many branches as you want. In this case, I know I only have two because it's either the cold medicine or the placebo. Okay, and we're gonna see it's gonna wind up being kind of like a sideways tree, like you can picture a Christmas tree. There's the star on the top of the Christmas tree. Okay, and then after we have the cold medicine or placebo, then we have whether or not they're cured or not cured. And that's true in either case. Okay, so half took the cold medicine, that's 50%, and half took the placebo, that's also 50%. Then it says they found that 80% who were given the medicine were cured after a week. So looking at the cold medicine, 80% were cured, which means what percent were not cured? Well, if 80% were cured, then the opposite must be true. The complement must be true. 20% were not cured. That's 1 minus 0.80. And then it says, but they also found that 25% of those who took the placebo were cured. So this would be 25%, which means that 75% were not cured. And now what I'm going to look at are what I call the presents. So that's like the end result of each of these scenarios. You could have either had cold medicine and you're cured. So when I say and, that means multiply. So 0.5 times 0.8 is 0.40. You could have the cold medicine and still not be cured. 0.50 times 0.20. You could have the placebo and be cured. I think that's 0.125. No, that's not true. Oh, yes it is. I'm not stupid. All right. And then you could have the placebo and not be cured. And so these are all of the possibilities, and these are the things that we work with, the presents, right? When we look at a Christmas tree, the thing that we really care about are the presents underneath the tree. So the question is, if you take the medicine, so looking only at the medicine ones, these two over here, what are the chances you are cured? So in this case, I'm going to write my probability statement with words. Given I take the meds, what's the probability I'm cured? So this is my given, which means this is my denominator, all the ones that deal with medicine. These two. Okay, those are the medicine ones. And then my numerator is where they come together, the both cured and medicine. So only looking at these guys, which ones are cured? That's 0.4. Okay, and I type this in my calculator, and I get 0.8. Okay, the next one, if you are cured, what are the chances you took the medicine? Sounds very similar, but it's actually the reverse, because I'm given that I was cured, and I want to know, okay, did I take the meds? It's probably not me, somebody else. So given the cureds, here's cured, here's cured. What's the probability I took the medicine? So of these two cureds, because that's what I'm given, that's what I'm looking at, which one showed taking the medicine? That's the 0.4. And that's a 76% chance. So they sound pretty much the same, but they're a little bit different. And we use the tree to help organize this information. So if you get a big paragraph where there's a lot of dependent probabilities, meaning one relies on the other, if this happens, then it's this probability. If that happens, then it's this probability. That kind of dependent probability kind of clues me into saying, let's make a tree. All right, so you might see again down here. 12% of Chicago's population is over 60. If you are over 60, there's an 80% chance that you own your home or apartment. If you're under 60, there's a 46% chance you own your home or apartment. If you're renting from a homeowner, what are the chances your landlord is over 60? Okay, so right now pause the video and try to make the tree yourself. Okay, so let's check this out. So it looks like 12% of Chicago's population is over 60. If you are over 60, there's an 80% chance you own your own apartment. So we're looking at, you're either 60, over 60, or under 60. And then based off of your age, there's a certain probability of owning your home or not own. Own or not own. Okay. So, if you are over 60, 12% of Chicago's population is over 60, which means 88% are under 60. If you are over 60, there's an 80% chance you own your own home, which means there's a 20% chance you do not. If you're under 60, there's only a 46% chance you own your own home, which means a 54% chance of not. And then to finish the tree, we multiply across because we're saying this represents over 60 and owning a home. Okay, this is not the end. This is just to help us answer the question. Now the question says, if you are renting from a homeowner, so given homeowner, what are the chances your landlord is over 60? You might do this to figure out if you should email them or call them, you know. So given homeowner, so I'm looking at owning homes, so that's these two. What are the chances they are over 60? It's this 0.096. And so now we put these two together. And you get about a 19% chance that they are over 60. And that's conditional probability. You can see it in many ways. Anytime you're given something, you will use this conditional probability. Okay, you can also use it to answer independence or dependence. These really aren't the only ways that you can do conditional probability. It can show up in any format. So back when we were doing Venn diagrams and we saw, okay, the probability of, owning a dog is 40% and a cat is 30%. And sorry about that, hang on. probability of owning both is, I don't know, maybe 10%. You can still get a conditional probability question where it's like, what is the probability of owning a cat given you own, or a person owns, a dog. So you may still need to set up the Venn diagrams to fully understand the question, where you're like, okay, here's dogs, here's cats, 40% own a dog, 30% own cats, and 10 are both. So then we find just this side and just this side, and we say, what's the probability of owning a cat given you own a dog? So we know our denominator is the dogs, which is this whole circle, 0.40. And we know the numerator is where cats and dogs come together, which is that 0.10. So this is actually 25%. Okay, so you can see conditional probability really in any format. It's just this understanding of the given being our denominator and the numerator being where they come together, that intersection. Okay, that's everything on conditional probability. Good luck.